Thanks, Afzal. Hi, everyone. My name is Shubham Chopra. I work at Bloomberg in a group called Foundation Services, along with my colleagues, Sudarshan and Joe sitting there. We predominantly focus on Spark and how we can use Spark for online analytics at Bloomberg. And I'll talk to you a little bit about that today. So I'll start with giving you an overview of what analytics at Bloomberg is all about, right? I will talk about what are the common patterns and how we are solving them for using Spark at Bloomberg, specifically around serverization of Spark. And finally, I'll talk about what are the common challenges that we face with using Spark for online use cases, right? So let's get started. Bloomberg is almost synonymous with financial analytics, and pretty much every trader would have Bloomberg Terminal on their desktop. It's a very premium product, and there's very high expectation of quality of service, the speed of analytics, and the quality of data as well. So analytics at Bloomberg are supposed to be this human time interactive. So I'm talking about analytics in, say, hundreds of milliseconds, right? The data stores are heterogeneous, so think along the lines of data stored in Solar, let's say HBase, RDBMSs, right? And often analytics may require accessing data from disparate sources, right? There's no notion of having a single data warehouse solution that would be used for large-scale batch analytics. It's all contiguous data, right? A lot of analytics tend to use both historical data and current data with almost equal frequencies, right? Along with this, given that it's financial data, it's also getting constantly updated, right? So there's this stream of update which may be at a different clip for different kinds of data, but nevertheless, it's always getting updated, right? So it's a reality of data updates happening is a reality of life. How do we see Spark getting used for analytics in such a scenario? Spark actually provides a lot of capabilities in scaling analytics horizontally, and this can give enormous scales, right? Spark, with its progression, it started off with RDDs, slowly is now moving to data frames, and data sources API that it provides, it's a pretty unique offering in that it unifies the way in which you access data from very different data sources. Now, a user does not have to be an expert in HBase or Solar to be able to meaningfully use those systems. Along with that, Spark streaming also addresses some of the streaming concerns we had about data updates coming in. Streaming actually provides primitives around update state with key and map with state in the newer version of Spark, which give you this notion of having a single state that gets constantly updated and which you can use to respond to queries. Apart from this, the biggest offering is what probably everybody here recognizes, which is the ability to cache large amounts of data on your cluster in RAM. And this is what gives you the capability to respond to queries in hundreds of milliseconds, if not less. So Bloomberg is looking to use Spark in an online setting, responding to online queries. And our solution for serverized Spark addresses some of the common problems around serverization, around reuse of Spark transforms, managing the life cycle of data itself, and handling streaming updates. So let's go over this from top to bottom. You have a request handler that routes requests to various request processors. These request processors would be, say, various Spark applications running and responding to queries. They, in turn, use a registry, which is a centerpiece of this that combines combines data frames with execution metadata and schema. And there's an ingestion manager that's taking care of making sure those data frames are up to date with the latest available data. So the key takeaways that I want you to get from this is that we are distinguishing transforms into two categories here. One is ingestion-related transforms, right, which create all the data frames and make sure the data frames are all up to date with all the updates that are coming in. And then there are query time transforms, right, which just use those data frames that the ingestion time transforms created and then respond to queries in, like I said, hundreds of milliseconds, right? Now, once we have that distinction, let's see what kind of production usage can Spark see and what kind of capabilities it has today for those. So we all know that RDDs were almost the cornerstone of Spark. When it came out, they stand for resilient distributed data sets. The resiliency of them actually comes from the execution lineage, which is stored in the driver. So if, let's say, you have some data loss because of a lost executor or a lost partition, it's the lineage in the driver that gets used to recompute that lost partition on the fly at query time, right? You definitely don't want to lose any data, especially at in production when you're responding to queries. So it does offer certain RDD replication capabilities, right? And I've given some examples of what exists right now. So you have these various levels that you can use to define persistence of data. So you have things like memory only 2, which would mean you're replicating your data twice, right? Memory only SER, which is for serialization. So serialize the data and keep it in memory. And then the other one is for 2 replicas of it. Now, Spark is enough plumbing to actually support any number of replicas you want, and it's fairly easily accessible as well. These are about making sure the data is available and some smaller problems around executor failures don't affect the data. Apart from this, for online performance, it's very important to note that a delayed performance can also mean, especially in an online scenario, delayed performance can also mean the system being down. Right? Both these things are in some way equivalent, especially when you're talking about online use cases, right? So around those, Spark does provide certain capabilities. So it has a notion of speculative execution, and it offers a lot of knobs that you can tune. The idea being that if certain executors are slow, right, you speculatively execute whatever tasks are running there, and that way you try to save up and respond to the query in some meaningful time, right? A common problem, a common reason executors tend to get slower over time is garbage collection. So with these things were introduced in 1.6 and are getting improved in 2.0. A lot of work is being put in to save data off heap. That way we minimize garbage collection stalls, right? So this is the state of Spark as of now, out of the box, right? What are the challenges with this? So we spoke about how RDDs are resilient because the lineages are in the driver, right? What if your driver goes down? You may have a 1,000 node cluster, right, that would be holding on to a lot of data. If your driver goes down, you lose all of that state. You would have lost all the data there. If, let's say, you want to bring the whole thing up again, you would have to reconstitute the cluster and reestablish that state, right? A very naive solution to this problem could very well be, let's have two clusters running simultaneously, right? It's still problematic, especially in our kind of use cases, because we don't want queries to return inconsistent responses. So if, let's say, you have 2 servers, full-fledged servers running simultaneously, a user fires one query, and let's say the user fires the same query twice, it may end up on both those clusters, which in turn may have gotten the data snapshotted at different time intervals, resulting in maybe slight discrepancies in whatever response they give. this kind of a scenario is unacceptable to us. So the naive model, and we'll talk more about this later as well, doesn't quite cut it. Even with high availability of RDD partitions, especially when you, let's say, have your entire data set cached in RAM, lost RDD partitions can still kill your performance because these partitions tend to get recomputed at query time. All in all, there would be some performance consistency issues, and your performance is very often gated by the slowest executor. You're as fast as your slowest executor. And again, because slow responses for us means non-availability, we clubbed together high availability and low tail latency issues together. And that's the reason they are actually very closely related. Now, having looked at these challenges, let's discuss a strawman approach, like we were talking about, having full-fledged clusters running simultaneously. So let's say in this scenario, you have Spark server that I showed you earlier, and multiple instances of it running simultaneously, and each one of them being backed by a full-fledged Spark cluster that is getting its data, and it has its own ingestion manager that's hydrating all the data. So all the Spark clusters are in some sense, they're up to date with all the latest data they could get their hands on. Now, what could happen is, let's say, two clients, the scenario that I described, could send queries to different servers simultaneously, resulting in some data inconsistencies. To avoid a scenario like that, what we could do is, have a system like Zookeeper that can help us with leader election, right? We could have, so we have n Spark server instances running. We could have a single leader elected, and only the leader responds to queries. So if a client contacts the leader directly, the leader executes the queries, and it responds back. If a client happens to contact a non-leader just simply redirects the request, right, and responds to queries. This way, you still have Spark servers to fall back on, and should the leader here fail, right? But there won't be any data inconsistency because all your queries are still getting responded to by the leader itself, right? Is that the ideal solution? Not quite, because your leader is now, again, the single Spark cluster that's responding to queries. So all the RDD partition loss issues are still present, right? Again, you are as fast as your slowest executor. And now you have resource usage that's amplified by the number of Spark servers you're running. So you now have multiple Spark servers that are in some way doing busy work, while only a single leader is responding to all the queries. So how do we get across, how do we solve some of these challenges? Before we get to that, let's have a quick overview of Spark architecture and the way things are kind of wired inside Spark, so we can talk more informatively about it, right? So this may be familiar to a lot of people here. Spark has a master worker architecture. There is a driver, and then just for example, I've shown two executors here. And an RDD is referenced only in the driver. An RDD, if let's say it's cached in memory, let's, for example, take an RDD that has two partitions. The way things work is this RDD would hold on to references to two partitions. In this example, one partition being held in executor 1, the other one being held in executor 2, right? Now I've used a notation RDD block. This is actually how Spark stores partition. For the sake of this discussion, we can assume that there's a one-to-one correspondence between RDD partitions and RDD blocks, right? There's a slight nuance to this, but can be ignored for this discussion. These blocks are held on to something called a block manager that's run inside each executor, right? So every executor has its own instance of block manager running, which holds on to various data structures that hold on to RDD blocks, right? Now, each executor talks to the driver and has its state known to the driver through an RPC environment that constitutes block manager master and block manager master endpoint, right? So that is how RDDs get stored in Spark. Now, how do RDDs get replicated? Let's quickly go over that as well. So let's say we have the driver, we have two executors. RDDs only get computed at query time, right? So let's say if you want to cache some RDD, you call a simple function on it like say count. When you do that, the driver asks the executor to compute that RDD. Now what the executor would do is compute that particular partition that the executor is responsible for, and it would hold on to that partition. And let's say you want to replicate that partition multiple times. So this executor will then ask the driver, hey driver, give me the list of all my peers. I want to replicate this block. The driver responds with a list of all its peers, and this executor would randomly choose how many ever replicas you want. It would choose that many number of peers, and it would send that entire computed block to that executor, right? That executor would store that data, and once it's convinced that the data is replicated, it would send the results of computation back to the driver, right? So this is the state of data replication as it is today. What are the challenges with this? Lost RDD partitions are pretty costly to recover, and this data replenishment, because of Spark's lazy nature, happens at query time. Now, oftentimes, Spark is also run on top of resource managers like Yarn. And with Yarn, you can have multiple containers on the same node, and you could have multiple Spark executors running on the same node. Now, even if you try to replicate data, both your replicas might end up on the same node because the replication is all completely random. Let's take it a step forward. Your replicas might also end up on the same rack, right? So in an online setting, this makes your system very susceptible to node or rack failure in spite of you having replicated your data. What's more, lost blocks this way through node failure or rack failure, they are not replenished proactively either. Everything is supposed to be lazy. So to address some of these challenges, we opened up a Jira, Spark 15352, for topology-aware data replication. And the pull request for this is already up. We developed a solution where we are making data replication pluggable in some sense. So the key issue around selecting peers, we have tried to make it a more generalized solution. And in our implementation, we say that the driver gets topology information on all executors, right? And each executor is told about this. Now, whenever executors ask the driver for peer information, right, we decorate this topology information with that, and the executor now uses a prioritizer to prioritize the list of peers it got to make sure there are certain data replication objectives are met. This way, ensuring should your topology require data replication in specific ways, you could plug in your optimizer to do it, plug in your prioritizer to do it for you. The default implementation we have out there, it replicates Spark's current default behavior, which is random selection. This is actually a multi-part Jira, and there are several dimensions to this problem as well. So depending upon your topology, you could have different replication objectives. So for example, let's say you could have, you would want to replicate to different hosts. So you want to make sure the replicas you have don't end up on the same host, even though there may be multiple executors on the same host. So you can specify that as an objective. You can specify an objectives where if you are familiar with HDFS, these are very similar objectives to what HDFS has, which is having a replica on a node, having a replica within the rack, and then having a replica outside of the rack. The way you specify them would be dependent on the topologies that you're running, right? This is something we have under development, and we should put it out pretty soon. Now, you should note that different subsets of peers could satisfy the objectives, and you can put in an optimizer that finds the minimal set of sorts, and if you replicate to just this minimal set, your application objectives are met, and at the very least, you would not be as susceptible to node or say rack failure, or depending upon your topology, any failure that you might foresee. The third part to this problem is proactive replication of, proactive replenishment of lost data. So this is something we envision the block manager master endpoint, which was housed in the driver, which knows which executors are up and running, and through heartbeats and such. It would know that an executor has failed. It would know the blocks that existed on that executor, and the replenishment, very much like it happens in HDFS as well. The HDFS knows a node has gone down, and certain blocks are under-replicated. So it tries to, picking a suitable time, it tries to redo the data replication. So we envision, we are trying to put something of that sort into Spark as well. So even if you lose certain replicas, even if you lose certain partitions through node or rack failure, your block manager master endpoint is able to trigger replication. So this addresses some of the problems around data replication. We also spoke about how Spark driver itself also needs some hardening, right? So let's look at some issues around Spark driver now. To start off with, Spark driver, you can look at it as a general Java or a general JVM process, right? Now, not all the state inside this process is interesting to you. Specifically for the online use cases that we've been talking about, only a certain subset of this state is interesting, and only a certain subset is the kind that actually is pretty expensive to regenerate, right? For these specific use cases, you might have a bunch of RDDs or data frames that you've ingested, and because you have them cached and these are expensive to regenerate, you might want to in some way hold on to that state if possible. Now, when you're doing that, expressing your operations as RDDs, expressing your transforms as data frames, it kind of gives you a separation, because your transformation is now expressible in the form of a succinct logical plan that can be very easily serialized and moved around, as opposed to, say, RDDs that result into, or transforms that are created by RDDs which are in the form of bytecode, right? So it becomes very easy to move any data frame based transformation around to multiple machines. So we spoke about some interesting state in the driver, right? Let's get a little deeper into that. So some of the interesting state in the driver is the block manager master endpoint itself. Now this keeps a track of what blocks exist on what executors and what executors are currently on. We spoke about how data frame kind of separate this logical plan versus and separate that in a better way versus, say, RDDs. Spark SQL core has a component that's called the cache manager, and what this does is it actually you can actually cache on to some computations that you've run, and this maps a logical plan that you put in with that data. And the intention is that should you submit a larger logical plan later on, it will try to short circuit either the entire plan or portions of the plan with pre-existing results if it can find any. So all of this is already inside there. So the cache manager state itself is a pretty interesting thing that you would want to hold on to, right? Apart from this, Spark also has a job scheduler that keeps a track of various stages and tasks that have been scheduled on the cluster. And there are some queuing semantics also available around it. This is another component which would be very important in keeping a track of what kind of queries are currently running and how much of them are over. Apart from that, there is a general executor information around what host name and ports executors are running on. So this is some of the state that's pretty interesting, and some of it may be very hard to reconstruct. And I should point out this is illustrative and not quite an exhaustive list, right? Now, what if we externalize this driver state? The benefits may be if you, let's say, put all this state, let's say we are able to magically do that and we put that state in some external source. What are the benefits we get? We would be able to very quickly recover from even driver failures. Your new driver comes up, it reads the state, it knows where all the executors are. You don't need to restart executors, you don't need to reconstruct the state. You're back where you started, right? What's more, you could take it a step further. You could now have active drivers which are synchronizing on the state. So you don't even have the downtime of a single driver going down and you're trying to bring it back up, right? Now, in what way, I said, let's magically solve this, and what are some real solutions that are available for this? One of the solutions that partially solves this is off-heap storage of RDs itself, something like, say, Tachyon, but that is only limited to storing the RDDs themselves, so it only stores the data. There's no other state being held there. What if we add, residual bookkeeping from the driver? What if we store just that portion of the state into an external system like, say, Zookeeper, right? Just to make it clear, only the bookkeeping state is being put into Zookeeper, okay? We kind of come to a system like this. What if we have, say, a quorum of driver? And these are just some of the discussions we've been having. Just thinking out loud here, some of the things that we are discussing and trying to come up with. So everything pretty much in flux, nothing set in stone. So let's say you have multiple drivers that share a pool of executors, right? Let's say we spoke about ingestion transforms earlier, right? Let's say you fire a transform on driver 1. It in turn creates RDD blocks on, say, one executor. And currently, once that block is created, the executor tells just one driver that it's created that block. What's to stop it from telling that state to 2 drivers now, right? So now both these drivers are aware of that particular block existing on this one executor, right? We put that, let's say the ingestion state was put through cache manager. So cache manager is also now aware, and we make sure we synchronize state in cache manager as well. So now cache manager also knows, certain logical plan was computed and it's available. We also keep job scheduler outside, and job scheduler then provides your usual queuing like semantics. And let's say now we get a query, which is an application query that's supposed to use this data we ingested. So this query would come to any one of the driver. In this case, I'm showing that coming to driver 2. It goes to the cache manager, which had all the state ready with it. The cache manager then tells the job scheduler to schedule a job, right? And the job scheduler uses the same executor pool. Now, you could as well have another query coming in. As long as you have the same job scheduler, you should not have multiple drivers stepping on each other's toes. Just a hypothetical scheme that can solve some of the challenges we talked about. And with that, I would like to end, if you guys have any questions.
So I have a question. How do you actually get the data out of the RDD? Are you using like indexed RDD, or like when your requests come in, you do it like a key by key case, or how does the request manager actually get a per key value?
So
Could you repeat the question for the folks?
sure. So the question, if I understand it right, is we get a query and we are interested in just a single key of the entire data set you have. Yes, index RDD is a potential solution. We are mostly talking about large-scale analytics, though. So these are more analytics of the kind that look at a significant subset of the data to compute things. So think along the lines of, for example, let me give a financial example. You have 1,000 companies and you want to find the average stock price for whatever reason. You'd have to look at a lot of data points, pick something out, and then do some computations on top of them. So it's not a find me a needle from a haystack kind of problem. These analytics are slightly wider than that. I think that's it. Thanks, Shubham.
So while we do the switch here, I don't know if you guys saw the pizza came in. So why don't you guys feel free to grab a piece of pizza, come back, sit down, and then we'll get the day going in next set of
I just sent you guys a note. I just sent you a note.
Yeah.
Let's not post Shubham's slides publicly on Meetup. So we inadvertently made a reference that should not have been public. Have you posted it already?
No, but we're live streaming,
We're live streaming. Yeah, we can't help that. But
so we haven't posted them though.
okay, let's please hold off on that.
Okay.
I'll give you an edited version of it by latest by tomorrow, and let's post that.
Yeah.
Okay. Yeah, it's a reference that shouldn't have made it out in a public document. We didn't pay careful attention to it.
Okay.
Yeah.
There's some left after it for us. So let's start with running Spark in production. So this is a talk that I did at Hadoop Summit in Dublin a couple of months ago. So if you have seen that, my apologies. I'm assuming you're not there. So who am I? I'm Director of Product for Spark at Hortonworks. I've been involved with Spark for 2 years, for Hadoop 3 years. I'm also contributing to Zeppelin, and you can follow my blog, etc. So I'll cover 2 topics. One is security, one is performance tuning. And both topics are very important if you're trying to run Spark in production. So, and a lot of it in Shubham's session, he covered a lot of internal details. Let me step back and talk about what are the different deployment modes of Spark and set the context for the rest of my session. So Spark technically supports 4 different cluster managers. 2 of them I haven't listed here. One is Spark pseudo mode, where everything is pseudo, meaning it's all in one node. Everything is running in one, and it's basically for development, etc. And it's not really an environment you'll choose for production. The other one is Spark standalone, where Spark itself is acting as a cluster manager. The third mode is Spark on Mesos, and at Hortonworks, we don't focus on Spark on Mesos. The fourth mode is Spark on Yarn. So this is all Spark on Yarn. And even Spark on Yarn has 2 sub-modes. One is Spark cluster, or rather Yarn cluster. The other is Yarn client. So what's the difference between these 2 modes? So let's step back and talk about what is the anatomy of a Spark application. So there is the Spark driver. The driver is responsible for compiling the when you do a Spark summit, the driver takes that job, compiles it to stages and tasks, sends it to the cluster, and coordinates with the executors, get the results back in the driver. Now, depending on where the driver is running, whether the driver itself is running inside Yarn or the driver is running outside of Yarn. If the driver is running outside of Yarn, that's called the Yarn client mode. If the driver is running within the Yarn, that's called the Yarn cluster mode. So that's sort of like the background. So let's double click on that, like what happens. So when you do a Spark summit, and this is, again, I'm just focused on Yarn here. So your driver contacts Yarn. The resource manager is saying, I'm going to launch a job. Give me X amount of executors that I'm asking. Yarn consults its policy, whether this user is authorized to launch jobs, etc., whether there are enough resources in the cluster. Assuming all that is true, then it launches a container inside a Yarn container, and this is a special container. It's called Spark Application Master, and then depending on the number of executors requested, those executors are launched. So that's sort of like the anatomy of what happens typically when you launch a Spark job. But I said this talk is about security. So let's now, with that context, talk about security. So if you know security, there are sort of like few presumptions built into the security. Like, for example, before I talk about AAAs and encryption, I'll say the first presumption is the network is secure, meaning you're not allowing some random unauthorized people access to your cluster, because that's the basic step. And I just want to add that for the completeness sake, because don't overlook that. So that's the basic step. Make sure your cluster is protected and only authorized people or processes have. So don't forget the network level security. Now, once you have that, Spark leverages Kerberos for authentication. So, and that's the Kerberos, my attempt at signifying Kerberos there by the 3-headed dog that Kerberos stands for. So authentication is based on Kerberos. So let's take a detour and say, look at what does Kerberos means for Spark, and actually what does Kerberos mean for in general. And so Kerberos is a 3-legged dance. There are 3 parties involved in Kerberos. One is, the first party is client. The second party is Kerberos service, or people call it Kerberos Key Distribution Center, the KDC. Think of it as the Kerberos server.
And the third party in the dance is the actual service that you're trying to access. So there are three parties, the process or the human being that needs to access something, Kerberos server, and the third party is the actual service or resource that you're trying to access. If you're familiar with something like OAuth, this is like, oh yeah, I know the three-party dance. So that's sort of like Kerberos. So step one is the client, and this can be a human or an automated process, can do a KInit, gets, and the KInit and provides its own credential. And typically, the credential can be a username and password or other things if you have configured. The client will take that credential, go to the KDC, and validate that credential. The KDC, if the credential is valid, will issue a ticket. This is the master key. It's not the key, it's the master key. It's the key to a key. The client will store the master key locally in its own cache. That's step two. Now the client is saying, I need to access, say, let's say, name node or HDFS name node. In that case, the client will basically do a key exchange. It will say, given this master key, I need a service key for the name node. And that's step three. And then that's the client then talks to, again, KDC, exchanges that. The client then, once it has the service key for name node, will then contact name node and saying, I want to read this file. Name node has a mapping of the file name to the blocks in HDFS, et cetera. Name node will consult all that information and will, along with the block location, it will also issue a block access token. So that's sort of like step five. Now, from this point on, the client is directly talking to the blocks in question. The block access token is encrypted with a symmetric key. And so client is then talking to data node where the block is and sending its block access token. So that's sort of like what happens under the covers. And because Kerberos protocol takes care of a lot of these interactions, as a user, you did a KInit, or if you had a key tab and you're running a Spark Summit, you specified the key tab and the principal name. All this interaction happens under the cover. So let's bring that information to transpose that to Spark. What happens? So as a client, you come in as a user of Spark in a Kerberos environment. You come in, you do a KInit, and then submit a job. To submit a job, you need to have already a valid Kerberos service ticket. That service ticket is sent to the Spark application master. And let's say in that Spark job, you're trying to read some data from HDFS. So on the previous slide, I described the interaction to get to the HDFS service ticket. All that happens under the covers. And then let's say the user here was John Doe. Then the job is being accessed using the block access token that was issued with the John Doe's identity. So HDFS will get John Doe's identity and will either allow or not allow access to those blocks or files based on what is configured as the access policy in HDFS. So that's sort of like the basic interaction that happens when you are dealing with reading data in a Kerberos-enabled environment. So here I gave the example of reading data from name node. If you happen to be reading data from some other X data source, that interaction should happen. And the caveat there is whether X implements this control. So here is an example of running Spark in a Kerberos environment. You do a KInit as John Doe, specify the key tab, and once you submit in the same shell, if you submit a Spark job, the same identity specified by the key tab is used. If you didn't specify a key tab there, you can put it in the command line as well. So that was authentication. The second A of security is access control or authorization. So when John Doe submits a job, the job goes to Spark cluster or Yarn cluster. And the first control is, can the user launch that job? So within Yarn, there is an access control happening. Does user have access to this Spark or this Yarn queue to which the job is being sent to? That's step one. The step two is does the user have ability to launch these executors. So all that check happens within HDFS now, or rather within Yarn, and let's say that job is reading from HDFS. Then the third access control is, does the user have access to read that data from HDFS? So you can configure these policies, access control policies, within Yarn or HDFS at the component level individually, or you could use something like Apache Ranger to configure all that centrally from one node. And in a typical enterprise environment, like people want to do things once from one place. So like I'll highly recommend using Ranger to configure your access control policy. So that's sort of like how it happens for access control. So this, if you're reading data from HDFS, then HDFS access control apply. If you're reading data from some other third party, let's say MySQL. So in that case, you're reading data from MySQL, which is hidden behind the data source API. So you'll need to provide your own credential, and hopefully that data source takes that credential and uses that credential for access control. So if you're, so that's something to keep in mind. Now, the third A of security is access control, or rather auditing, because if you're running Spark on Yarn, all the access control is automatically audited by Ranger, and HDFS and Yarn also provide audit. So I have skipped all the auditing thing, but all the audit information is there and available in Hadoop as well. And you can look at it through Ranger or whatever other access control mechanism you're using. So now jump into encryption. So typically in encryption, if you look at the high topic of encryption, there are two subcategories. One is encryption in motion, and the other is encryption of data at rest. Data at rest is as the files encrypted in the file system, and data in motion is basically what happens at the transport layer. So this, on this slide, I'm talking about data in motion or transport layer security. So when you do a Spark Summit job, and I've tried to color code different things, my apologies if the color isn't very clear. So some flows are control flows, and the other flows are flows where actually data is being transferred. So all the purple flows is control and RPC, and the black arrow is the driver talking to the executor. So for example, if you send with your Spark job some files as part of your job, or if you're doing broadcasts, that data is being communicated over the broadcasts over HTTP. So you can configure SSL or HTTPS there. If your executor is reading data from some data source, so for example, in where we are talking executor reading data from HDFS, you can enable HDFS transparent data encryption for file system for the data at rest. You can also enable the web HDFS SSL encryption, so you can read data or in motion as well, or encrypted. But if you're reading, if your data source is not HDFS, let's say it's MySQL or some other proprietary database, then you have to make sure that database is listening in SSL or encrypted mode, and you pass the right through the driver the right connection string to connect to that. So that's sort of like the green channel between executor and data source is data source specific. So now so Spark also, the executors, let's say executors have some shuffle data. An executor can go away. So what they do is, specifically with Spark on Yarn, that data is stored locally, and then that data is sent when another executor needs that. The other executor reads that data from node manager. And also, when executors themselves, when they are fetching blocks from another executor, that's the orange arrow, and that's shuffle block transfer. So let's look at, depending on these things. So on the previous slide, I had the color coding. Here is color coding mapped to what exists for encryption and how you can enable that. So for example, control RPC, you can set Spark authenticate, and that is based on symmetric key. With Spark on Yarn, Spark leverages Yarn to distribute the keys. If you're using some other cluster manager, then you have to manually configure what encryption keys, etc. Shuffle block transfer supports SASL-based encryption. It doesn't yet support SSL. Read-write data, again, depends on the data source. So for HDFS, you can encrypt used HDFS RPC-based encryption, or if you're using SSL, you can use the Web HDFS protocol to read. So practically, like for example, for Web HDFS, what does it mean? Wherever you're specifying in your HDFS RDD, the location of the RDD, you can specify that with the Web HDFS protocol or Web HDFS over SSL protocol. For example, and the other part, the black arrow where the broadcast or the file download was happening, Spark uses SSL for that. So what are some of the gotchas, or some of the things we have found that have either tripped over a lot of people or we know of active issues? One example is if you're using Spark SQL, a lot of time people access Spark SQL using the Spark thrift server. So Spark thrift server is sort of like based on Hive's thrift server, but it's sort of like a copy that was forked from Hive about 2 years ago, or maybe even more at this point. And it didn't have any identity propagation enabled, and that is still an issue right now. So your client can connect to the Spark thrift server, authenticate itself. Spark thrift server doesn't send that identity downstream. And that's problematic because downstream, you don't know who the user was. So I would recommend if you are first be aware that this is an issue. The workaround would be use Spark SQL via the shell or the programmatic API. And in that case, the identity is propagated. But it's not. This won't work if you're trying to put a BI tool on top of Spark SQL. So that's the problem. I'll skip the second bullet because I have 2 more slides that talk specifically about that. Spark on HBase, there were issues with Kerberos token that was fixed with Spark 1.4. Spark streaming and Kafka with Kerberos with SSL. There were a bunch of issues. We have fixed them with HTTP 2.4. So if you're on 2.4 or higher, this Spark streaming with Kafka and Kerberos should work. And Kerberos token not being renewed for Spark jobs over 72 hours, that was another issue that was fixed. So I'm talking about now what are we doing for securing Spark SQL. So if you're coming to Hadoop Summit later this month, you can come see a live demo of this thing and we'll talk more about it. So I have a session at Hadoop Summit talking about state of security in Spark. So I'll go in more details and show a live demo there. But essentially, if you're trying to access Spark SQL today, you can have either of file level access of Spark SQL, but there is no fine-grained security available with Spark SQL. And fine-grained security implies like row level, column level access or masking. So that's the security that exists with Spark SQL today. What we are trying to do is integrate Spark SQL with Ranger and LLAP. So Spark SQL can talk to something called LLAP that we are working on. So a tech preview of this, I'm not saying that we are doing GA soon, but a tech preview of this feature is going to come, and you can see a demo. So what you will get is in your Spark SQL, you'll have to modify 1 or 2 lines of code to have a specific setting in your Spark SQL context, and then we can take advantage of those configuration and redirect that query through LLAP to read the data from Hive, and then the same policy control that you have. And again, you can configure the policy for this through Ranger. So not only you can have row and column level security, you can also have masking. So let's say, imagine you have a table and one column is social security, and then you have multiple groups saying admins or marketing, and you don't want marketing to see the social security. You can create a policy through Ranger saying don't show when marketing people are querying this table, show the data in the SSN column as masked, so you can do that. Or you can say sort of hide some rows from marketing. So maybe show certain sort of like SSN, but not all. So, or you can even hide certain columns from marketing. So all that is possible, and we'll show a demo of that. So the second section of this topic was performance. So one of the questions I frequently get asked, and I'm giving a very high level sort of like rules of thumb. It's basically a starting point. It's not where you will end up, hopefully, but this is a starting point. So one question people often ask is, should I create a small executor, or should I create a lot of big executors? So essentially, the answer is, we had to run some tests because we had that question ourselves. So in this example, I have 3 nodes, total 24 cores each, and 96 GB memory. So I have total of 72 cores and 288 GB memory. And I configured, my colleague Jerry here, he ran all these tests. So we configured to take advantage of all the memory and executor cores. And we ran different configurations, and we ran some tests. And what we found was, and you can see the performance varies slightly depending on the executor size, how much core was allocated to each executor. But essentially what we found is the performance, unless you're trying to allocate a really big executor or a really small executor, for medium side, the performance is relatively constant. So that's a key thing to note. So what is the takeaway? Unless you have a specific reason, avoid a really big executor, avoid a really small executor. And what is the medium range, happy medium, which is somewhere along like 10 to 40 GB of memory per executor, and along like 3 to 6 cores per executor. And that's sort of like, this is a preferable choice. This will give you sort of like, if you have a really big executor, what happens? There is excessive garbage collection. And I think with off-heap storage, some of this may change, and we may have to redo all these tests as well. But for now, like, that's the best thing. If you have a lot of small executors, you're not taking advantage of the memory efficiency. So the other question I get asked is I have an executor with, let's say, size 4 GB. How much actual data is that storing? So the rule of thumb is, if you haven't changed any of the default sort of like properties, it's about 54% of the executor memory. And how do you get to 54? It's a multiplication of 2 default setting, 0.9 times 0.6. But around 54% of the executor memory that you have allocated is used to store actual data. So don't confuse executor memory with the actual container memory and with the actual amount of data that you're storing in that executor. So obviously, like 10% overhead, whatever is the memory for that executor, 10% will go to the CPU scheduling, et cetera. So these are some of the things to keep in mind. And again, there's some resource here for CPU scheduling if you need to sort of like put limit on how much CPU you want to enable, CPU you want to allocate. Then the other question I see is, what task parallelism should I set there? And that's sort of like on the group by operations or reduce by. And this in your mind should trigger, oh, these are reduce side operations. So task parallelism applies to reduce side operations. So on the next 2 slides, I'm kind of like saying the same thing. Task parallelism here is controlled by the number of reducers. So the question then is, should I increase the task parallelism or should I reduce the task parallelism? So that's basically the question you're asking. So because Spark is really efficient in sort of like farming out new tasks and scheduling those things, you should try to have as many like tasks as possible. So you should have, to take maximum advantage of the cluster, you should try to maximize the number of tasks. And if you remember the previous 2 slides, this is essentially try to, on the reduce side, have a wide funnel. And what this does is it will try to reduce the data skew. So I'll summarize this point as saying, prefer a lot of small tasks rather than having a big task. In the big task, when you have reduced the task parallelism, and as a consequence, your particular reducer is trying to move a lot of data into that particular reducer or executor, like if the block size is too big, over 2 GB, I've seen some crashes there. So we again ran some benchmarks, and we saw sort of like in the middle range, if the task parallelism was up to 10 times the number of cores, we got good performance. So you can have sort of task parallelism up to 10 times the number of cores that you have in your cluster. So what are the conclusions to draw from this point? Again, like Spark, in that sense, like learning the API is very easy. But once you try to optimize it, you got to really understand the workload. And for that, it's once you understand the workload, once you understand how Spark works, it's at that point you can get the maximum advantage out of your, or maximum performance out of your job. So the better you know the framework, the better luck you'll have in tuning that. Cool, thank you. Questions? So the question is, what's the relationship between executors and containers? And is there more than one executor per container? So as far as I know, and I have here more of my experts here. So as far as I know, there is only one executor per container. And the container here is something that is given by yarn. So it's a yarn sort of like unit of allocation. I think you're trying to talk about the proxy user. So if you're launching the job as A, but you want the file access to be read through a different user?
Well, it was changing users between nobody and the Unix user.
Yeah.
And so, yeah, it was actually like, it seemed very insecure to me. So, but you were talking about security. So.
No, so I'll actually go slightly deeper in this topic. So what happens in Hadoop in general is there is a setting called proxy user. And essentially, the proxy user is, as the name implies, if you're launching, if you're submitting the job as A, Hadoop launches the job as process A, as a user that, as a process that is owned by the user A at the OS level. But Hadoop is all Java. When you're launching the process, Hadoop needs to sort of like have a Java level or a system level privilege to launch the process. So there is a part of like container launcher, Linux container launcher, et cetera, within Hadoop that sort of like does, for a very short time, sudo, and then launches the process at that. So that's one level. And then the actual, at the runtime on that machine where the executor is running, the Unix account needs to exist for that user A so that the process can run as that user A. So that's one level. Then there is also configuration in Hadoop, and Spark runs on, when you run Spark on yarn, you get the benefit of that, is also which user on which nodes or hosts have the ability to launch these proxy users. So you can configure that to sort of mitigate some of those security risks. Okay. If there are no questions, we'll go to Zan.
John, in software in Hortonworks, mainly focused on the Apache Spark and the Hadoop ecosystem. and a contributor for Apache Spark, Young, HBase, and Barry. My experience is mainly on computer networks, distributed system, and the machine learning platform. Today, my topic is mainly on the Spark HBase connector. Before we go into that specific topic, I want to give a generic overview of the data frame in the Spark. Data frame, actually, if you follow the Spark from 0 point something, that at that time is the schema RDD. Then gradually, they transfer schema RDD to data frame, I think probably 1.2, not exactly, I'm not sure. Typically, the data frame is optimized by the built-in catalyst optimizer. Typically, when you write the Spark program, if you use the RDD, then you have to pay attention to those bottleneck. For example, group by K, reduce by K. You have to know exactly how it's implemented to avoid some traps out of memory. But if you are using the Spark query using the data frame, the Catalyst engine will help you to optimize the whole logical plan to pick up the optimal physical plan. So the end user doesn't need to pay attention to the internal implementation. That's the benefits. Then to improve the performance, then in later version, the Spark introduced the Tansen project. The Tansen project, I think, is still ongoing. Initially, it tried to use off-heap memory to reduce the garbage collection, also bring in hardware cache awareness computation. Then they use the code generation for expression. In Spark 2.0, to further push it to high level, they use a whole stage code gen. If you pay attention to Spark 2.0, whole stage code gen is very critical, especially for dataset. Because for dataset, it has to go through a series of encoder and decoder. But this whole stage code gen, through this optimization, you can see that most of the serialization and the deserialization are removed. So this. Then in Spark 2 1.2, they have the external data source. They introduced this one. Actually, this is a very great feature. You can integrate different external data source. For example, the CSV file, Avro file, Parquet, Arc, all those. Then when you import those different data into the Spark, they become the data frame. Then you can operate on two different data frames, no matter where it's from. One data frame may be from HBase. The other data frame may be from the Arc. These two data frames you can do join or aggregation to do any interactive operation. With the data frame in Spark, you can have two types of usage. One is you can write the Spark SQL. That's if you are familiar with the SQL query, select, count where, those conditions. The other is you can use it as a language integrity query. That's the data frame. Data frame you can filter with some condition, then join with other data frame. Then you can do the projection with the select. It's a high level, the data frame overview. Inside this data frame, including the 2.0 data set, the real engine is the Catalyst optimization engine. I think if you are familiar with the Spark Catalyst, this is a very popular diagram. Although the Spark code base is changing, evolving in every release, but the basic functionality, basic framework is not changed. Initially, you get the SQL query, select, start from a table, or you use a data frame, filter something. You get the unresolved logical plan. What does it mean, unresolved plan? You select start from table 1. What this table 1 means? It's just a symbol, a string. This analyzer will solve this unresolved relation, table 1, into a logical relation. That is where is this table 1 coming from? For example, if it's a Hive catalogs, then what file saves the contents for this table 1? Then what's the schema for this table 1? For example, what's the column for the table? Also, when you say select star from table 1, this star is a symbol. You have to solve it. This have to be solved to the all the column in the table. For example, ABC. That's what the analyzer doing. So you have the unsolved relation mapped to the solved relation. You have the unsolved attribute mapped to the solved attribute. Probably you have your UDF, function 1. They have to map this function 1 to the real class and instance of this implementation. That's the analyzing doing. After do the analyzing, you have the logical plan. Everything is solved. After you solve this logical plan, then you want to optimize it. This happened here. What is the optimizing doing? The basic idea is you select the table. For example, select ABC from table 1, where A larger than maybe some string. You want to do the filtering, push the filtering as low as possible. Ideally, you want to push the filtering to the physical plan when you scan the file. So that's the logical optimization. Eventually, after you get the optimized logical plan, the last one, you generate the execution plan. Execution plan is just the IDD DAG. In Spark 2.0, the physical plan, they append the name with the exec execute. Before that, actually the logical plan and the physical plan, they share the same name. It's very hard to differentiate, but now the code base is more user-friendly if you follow the code. The physical plan eventually is a build scan. What does it mean? You read the data from the external data source. Probably it's a file, or probably it's a Cassandra, or probably it's a HBase, whatever external storage. That's where when we implement the external data source, we actually specifically pay attention to this part. All of this part is done by the Catalyst engine. It's better if you understand how it works, but if you don't understand, it doesn't matter. You still can implement the last piece. Yeah, that's the external data source. It's just import the data from external storage into the Spark namespace. After you implement the full API, this data frame is standard. You can use any API available in Spark. The critical part, when you implement the external data source, if you go to the Spark code, you will find several of them build scan. It's based on your property of your external data source. You have to implement at least one of them. The first one, build scan, it doesn't have anything, just build scan. So it means this code has to read all the data from the file. There's no column pruning, there's no partition pruning, there's no predicate push down. It's the overhead, maybe there's not any optimization. You read the whole file, pass it. The second one, build scan, require column. There's a little bit of optimization. Your table maybe have 10 columns, but your query only need 5 columns. Here, you can, when you use the second one, you can read only 5 columns, forget about the other 5 columns. That's the 5-column pruning. The third one, you have 2 parameters, required column and filter. So at least you have the column pruning. You don't need to read the whole table or the column. The second one, you can push your predicate down to the physical storage. For example, if you are using awk, or if you are using Parquet, today we are talking the HBase. You push this filter to the region server. This is the predicate push down. Also, we use this one as the partition pruning. The partition pruning, actually, you read if you are familiar with the Hive, the file are saved in the HDFS, have some directory structure. For example, the directory may be the name as k equal 1. Then when you do the query, if you say k equal 2, then this k equal 1 directory will be skipped. This is partition pruning. But k equal 1 or k equal 2 actually is a filter, is a predicate. So this filter has two usages. One is skip some directory. The other is push this predicate to the native format or packet. Then they skip those columns, save the disk I/O. The last one, I haven't seen any implementation to implement this one, because the third one you have maybe some condition a equal to maybe a equal to 1 or a equal to 2. But the fourth one is very powerful. If your column is a nested data structure, for example, if your column is a structure type A, inside A you have the B, inside B maybe you have C. If your predicate may be A.B.C equal to something, these three will not have those filters, but this one is very special. It will have all the original filter. You can do exactly nested filtering push down. As far as I know, I didn't see. Probably, I think Elasticsearch, some people requested this feature. Yeah. But when you do all this build scan, it doesn't mean you have to do 100% accurate. You try your best, but you cannot lose any data. You can have the more data, redundant data. You cannot lose any data. As long as you bring in the data, the upper catalyst engine still do the software level verification to remove all the data. There's one option. For example, this you can point to the catalyst engine, say this filter is 100% accurate. So the upper engine can skip the verification. You can do that. But typically, yeah, I didn't use that one because HBase, typically I cannot achieve 100% accuracy. So this build scan.
I have a question. So the scan, does the scan only apply when you're trying to
Load the data.
content?
Yeah, actually that's the whole, when you created the external data source, this is a whole code you have to pay attention to. Everything goes down to here. Inside here, you based on your HBase or any external data storage to choose one of them. Choose one of them, then do the column pruning, all those stuff. Yes. Yeah. So if you are implementing the external data source, you choose one of this build scan. When you do the bring in the data, loaded the data into the Spark, typically partition pruning achieved by the build scan, column pruning, predicate push down. The other is the data locality. How the data locality is achieved? When you do the Hadoop RDD, the HDFS chunk, HDFS file, typically when you read the metadata from the HDFS name node, for each chunk you have the Hadoop RDD. For each partition, you have the preferred location. But when you construct your own RDD, that's what I did in HBase. The get preferred location, you have to explicitly set the host address to get the data locality. Okay, that's the overall high-level introduction on the data frame and how to implement the external data source. Now we go to some detail to the Spark and HBase connector. We use the Catalyst engine for query plan and optimization, as in that picture. Actually, we only pay attention to the last piece, build scan part. Then we use the HBase as a storage, key value store. then implemented the external data source API with built-in filter. We didn't leverage any coprocessor or any new filter. We achieved this performance with data locality and all those tricks in the query. We implemented the full-fledged data frame support. What does it mean? When you create this HBase data frame, after you load the data from HBase, this is the Spark data frame. Just forget about the HBase. You use it as a regular data frame to do join aggregation. We support the native Java primitive types. It means integer, short, long, double, floating, all those naive encoding in HBase, we can support it. We also support the composite key. In the row key part, you can have a component key. We support the Avro format. In the HBase key value, in HBase is just a byte array, but you can save it as an Avro format. Avro format means you can have a very complex data structure in the HBase cell. Then this complex data structure, Avro schema, we will do the automatically conversion between the Avro schema to the SQL data type. For example, this one. When we convert this Avro format schema to the SQL type, we will have a structure type, the first column, the second column, and the third column automatically. So next, actually, this is the most critical part if you want to use this Spark HBase connector. When we read the data, we have to have a mapping between the HBase and the Spark. What is this mapping doing? Which table you want to read? That, for example, here is table 1. All this column, which part is the row key of HBase? Here the row key is we specify as a key. Then we have a bunch of columns. The first one, column 0, 1, 2, 3, this is the Spark table column. This is in the Spark namespace. With each column, we have to map to the HBase namespace. In HBase, each column has a column family and a column qualifier. Then you have this type. This type is all the SQL type. Also, if you want to support the Avro format, you don't need to specify the type. We have another field, but I will not go into the detail. You can check the repo to find how to use the Avro format. So after this row key is reserved, means this column is a part of row key. All the other, just for each column, you specify the column family and the column qualifier. After you have that catalog, everything is easy and straightforward after that. Through the standard external data source API, if you are familiar with the Spark data frame external source API, this is the standard part. This is the standard part. Only this part, table catalog mapping. I think this is the only knowledge you need to know to use this connector. This is populated the data into the HBase table. After you populate the data, you can load the data to get a data frame in the Spark. This is quite standard SQL context read the option. Again, this is the mapping. You can see the only div part you need to pay attention to is always this mapping, catalog mapping, then the format and the load. After you load this data, you get this data frame. Then from here, there's nothing to do with HBase. It's the data frame operation. The upper one is some data frame language integration query, the filtering, select, projection. If you are not familiar with the data frame API, you use the SQL example. The first thing, you register this data frame as a table to the catalog. After that, you write your standard SQL query, select group by or some join condition stuff. That's the standard SQL query language. Yeah, the external data source API is really powerful. For this one, you use HBase is really good at point lookup through the data frame. Some other data source may be very good at for range scan. Then you have data frame 1, data frame 2, data frame 1 from HBase, data frame 2 maybe from Parquet or Arc. Then you can join. While you want the data saving in different storage, that's probably based on your application. When the traffic comes in, some traffic maybe you save to HBase. Some traffic maybe you save to HDFS. But here, Spark, you bring everything together to do some complex data analytical work. Yeah, this is a current community work because the current repo is hosted in the Hortonworks public repo, but we are migrating the code to the HBase chunk. Most of them already done. I think, yeah, this one is not latest. Okay, last one. Yeah. This one you can. This connector is a standard Spark package. You run, if you are running in the Kerberos cluster, it's the same as you run any HBase application on top of Spark. Typically, you use Kinit, or you use the principal or KTab. Then you can run this connector. It's natively supported by Spark. Yeah, that's my talk. Any question? Go ahead.
How do you handle inserts? Can you do like bulk loads from like a query?
When we do the insert here, yeah, the question is how do we handle insert? Actually, this we didn't specifically implement the insert, but for save, actually, it's quite similar to insert. We have the data frame. When we do save, or probably we change to insert, that's feasible. We actually, if the table already in HBase, we just insert into HBase, one record by one. Overwrite. In insert, you have several models, right? Overwrite true, overwrite false.
Like creating a table, you had to do bulk insert of like a large data frame.
Bulk insert, I think that is challenging because when you get the data in data frame, each partition doesn't mean this partition will go into the same region server. We have to do some shuffling to make this partition, shuffle them, then each partition go to the same region server. Then at that phase, we can do some bulk. Currently we don't support this one. Yeah. To support it, we have to do the shuffle, then do that work. Yeah. Okay. That's it. Thank you.
But the whole point of doing this work was so that you can be more efficient in connecting to Spark and do the predicate pushdown and partition pruning, and that's So thanks for coming out. I wanted to just point out two things. There'll be another meetup tomorrow night here. It's a hands-on meetup on machine learning with Spark and Apache Zeppelin. So if you're interested in that, please come out. It's hands-on, so bring your machine. And it's, it actually starts at 6:45, right? So come here and mingle, get something to drink, and then bring your machine, and we can start exploring machine learning with Spark and Zeppelin. The other thing I wanted to point out before we wrap up is so there's a Hadoop Summit happening June 28th through the 30th. So there's, I think, over 25 Spark talks happening at during the Hadoop Summit. So lots of activity there. Yeah. So thank you for coming up, and hopefully see some of you guys tomorrow. So thanks.